Swayam Prabha. Digital India. Educated India.
Okay, so jump, Markov process, binomial, Poisson distribution, right? Familiar? So we looked at a couple of reaction schemes where the solutions were given by binomial distribution or Poisson distribution. So we can go on further and then do more complex reactions as well. But I thought in this class we will take a step back and then just see that how and why these frameworks are useful. Okay, are they really useful? Do they really help us understand any physical system or a chemical system in reality? Okay, so today this is more of tutorial come lecture that I want to introduce a particular chemistry where the stochastic distribution is very important, without which we cannot explain the experimental observations. So I want to just bring that to light, so you could probably appreciate why we need this kind of a framework in the first place, right? So there's going to be some sort of chemistry. Just bear with me. I'll also try to make it as simple as possible. So what we are talking about today is fluorescence quenching. In a nanoreactor. So before we want to basically conduct a reaction where we have a molecule and we excite this molecule, it goes to an excited state and then it fluoresces, and then you can detect spectroscopically. Okay, you can measure the emission intensity at a particular wavelength, and then you can see as a function of time how this fluorescence decays over time. Okay, it's a very routine experiment that's done in spectroscopic studies of fluorescent molecules. Typically these are done in bulk homogeneous systems, but if you were to do the same experiment in a nano container or a nano reactor, the behaviors are very different. Okay, and that's where we bring this stochastic issue into this discussion. Okay, but before we go to the nano reactor, let's look at a simple chemical reaction that happens in a bulk situation and how we usually deterministically manage this modeling. Okay, so deterministic approach. So let's say there is some molecule A, and at time t equal to 0, we shine a laser. Okay, so we do what's called this pulse laser. That's a femtosecond, nanosecond laser that you can expose and then switch it off. That sudden impulse of light basically excite these molecules. The electronic states of the molecules get excited. Okay, and we call that is A star. At time t equal to 0, this molecule is excited, goes to A star. Then this molecule basically decays to a ground state. Okay, so this is called a radioactive decay. It emits light. You can detect the light, and then you can look at as a function of time how the concentration of A star goes down. Now this is a natural decay, but you can also have a parallel reaction. In chemical reaction we talked about we learned about series and parallel reactions. So while this can happen, you can also have another molecule which we call them as a donor D. Okay, and the D can also supply an electron to this so that it can decay like this. A star, ground state, excited state, one pathway. Another pathway, the same excited molecule can also extract electron from a donor and then acquire an electron, and this D become D plus. So this is called another pathway of decay. Okay. Now this reaction can also be reversible. So we can also write A minus plus D plus, giving rise to A plus T. So we can say that this is a rate constant Kf, Kq and Kb, I believe. Suppose if all this reaction were to happen in a solution, and we are interested in what is the concentration of A star is, okay, as a function of time, what we naturally do is we set up a law of mass action formulas, equations, where we say that the rate of change of A star is equal to minus Kf A star minus Kq like this. So there is a first order decay and there is a second order decay. Okay, so this rate depends on how much amount of donor we have. Now, if you want to assume that the concentration of D is much higher than concentration of A star at time t equal to 0, we can assume this second order rate into a pseudo first order rate. So we have minus Kf plus Kq D and then if you integrate this, you will see that A star at time t is A star at time t equal to 0 e power minus Kf plus Kq into D T. This is what we would usually do. Okay, so you can see that the signal or the fluorescence signal, which is representative of the concentration of the excited species, decay exponentially. Okay, and this is what happens if you do this reaction in a bulk system. For any given concentration D and initial concentration of A star, it exponentially decays. Okay, so we are happy. So now what we are going to do is, instead of this, we are going to conduct this reaction in a nanoreactor. So what's a nanoreactor? So nanoreactors are nothing but, imagine you have a bulk water here and then you put some surfactants. Okay, when you put some surfactants and when you reach a concentration beyond certain threshold, these surfactants self-assemble into a spherical aggregates. Okay, and one such aggregate can be something like this. So the surfactants are shown with this wiggly tail and a polar head group, and this is one such structure. Okay, and we call them as micelle, surfactant micelle. So this these are polar groups facing water. The inner part, this will be hydrophobic or non-polar. So the inner portion looks like an oil droplet. Okay, oil droplet. On the surface you have some polar groups stabilizing the interface, and then you have water. And typically the size of this can be up to the order of 2 nanometers or maybe 3 nanometer. Maybe you can make it a little bigger, may go up to 5 nanometer also. But typically they are below 5 nanometers. And you have many of them. Okay, and typically a micelle would have an aggregation number of roughly about 50. 50 surfactants come together and form this aggregate. So aggregation number is about 50 and its radius can be of the order of 2 to 5 nanometers. That's what I mean by nanoreactors. So here when we dealt with this, we looked at this reaction in a bulk water solvent. So now instead of doing that, we can do it in a micellar system. Okay, so you create this micelle, then you put this reactant A, donor D. Then what happens is that these molecules actually get solubilized inside this. Okay, in the previous case, in the deterministic case, the reaction is allowed to happen everywhere in the bulk homogeneously. But now we have created a micro heterogeneous system where there is a bulk outside and there is this nano container, and within this nano container, this entire reaction that I talked about happens. Then if you look at the fluorescent decay, it does not follow this kind of an exponential anymore. So what has happened? Whatever reaction that happened in the bulk that nicely follows this exponential decay, modeling wise, experimental wise, nicely matches. Okay. Now the moment I do this in a nano reactor where the reactions are confined within each of these droplets, and then I look at the fluorescence decay, that does not follow simple exponential decay like this. This modeling approach breaks down. This is not valid anymore. So then we say, okay, what happened then? It turns out that the molecules of A and D, or A star and D, they get distributed unevenly. There are some droplets which may have no reactant A. There are other droplets where there may be just one molecule. There are other micelles which can have 2 or more. So you basically have created a distributed system where the number of molecules or reactants are not equal anymore. They are finite and they are unequally distributed. Now if you take that into account and then if you go about modeling, then you see that there is a good match of the experimental data. Okay. So first what I will do, I will show the modeling aspect, how we will go about this modeling, and then later on we look at some experimental data and what I mean by all this A and D and everything. Okay, these are all corresponding to some chemical formula, very complicated chemical formula. We'll discuss that at the end of the class. Okay, is the context clear? What we are trying to do here? Yeah. Yes. Yes. So these are all independent containers. Imagine you have so much of batch reactor floating around. They don't interact with each other. Okay. Initially, you have put some molecules in each of this container, and the reaction is happening independent of each other. Okay. But what you observe as a outcome or the fluorescence is a collective sum of all of it. Okay. Now we want to take into account of that inhomogeneous distribution of molecules into the reactor and then build a model out of that. And that basically brings us to this stochastic approach, because no reactor are same. You got reactor with no molecule, you got reactor with one molecule, you got reactor with two molecule. You have to look at the ensemble of all this collectively and then see how the fluorescence decay is going to change. What is that? Geometrical distribution of? So these, okay, as far as the micelles are concerned, they are not spatially, they are spatially very well distributed. Okay, so the reaction does not depend on the spatial location. In fact, these micelles undergo Brownian motion because the size is 2 nanometer. They are executing Brownian motion even if you don't mix it, right? But reaction happening within the micelle does not depend on where the micelle is. Okay, so there is no spatial dependence of the reaction. Okay, which one? No, it depends on the local concentration. So if you have the fluorescent molecule inside the micelle, it will happen. If it doesn't, it doesn't. So, okay. So in this model, we are thinking about a well mixed system. There is no spatial variation of the micelle or the concentration of the species within the micelle. Okay, we imagine that these are well mixed reactor within, and there are many of them floating around. So now when this reaction happens in a micelle, of course the same scheme is happening, but here they are not happening in a bulk media, it's happening in this droplet. Okay, so for example, this can be shown that you have this droplet. Okay, I'm not drawing all the internal structure. Imagine this is one of the nanoreactor, and you have a molecule A star. Now I have put this molecule inside the microreactor, but actually they would be somewhere on the surface, okay, because they are I don't want to bring the electrostatic and the molecular detail yet, but imagine this is confined somewhere in the droplet, maybe on the surface or maybe inside, okay, it doesn't matter. So now there is a reaction rate Kf so whatever happened in the bulk, now it's happening inside a nanoreactor. Now this reaction imagine another droplet in which there is the excited molecule A star, okay, and let us say there is some I number of donor molecule, okay, this droplet contains I number of donor molecule. Out of that I, one of them will react to give A minus and D plus, A minus and D plus. The remaining I minus 1 is existing as D, okay. So again we are confining this reaction inside a droplet. Similarly here you have A minus, I minus 1 D and D plus KB. This gives rise to ID and A. So now considering this into account, let us write the equations. Remember that at no point of time any class of droplets, they do not interact with each other, they do not mix, they do not interact with each other, okay. Actually they do happen at a very long time scale, but suppose I am looking at the time scale where these reactions, quenching, all that happen, in that time scale we assume that these droplets do not interact, they are all independent reactor. Depending upon what they have initially, they can do any of these possible reactions. So this first term is a decay even in the absence of any donor. This is a natural decay. Now this term here depends on number of molecules of I in this droplet, okay, times the concentration with the rate constant Kq. So only these two terms survive, and if you note, I have written this index A star I. So what this means is, this is the concentration of species A star in a droplet that contains I number of donor molecules. Okay, now each of the droplet is now identified based on how many D molecules are present, how many donor molecules are present. I can be 0, I can be 1, I can be 2, 3, 4, etc., etc. Right? Now if I solve this, see, if you see this equation is nothing different, because this is the equation that we have got as if we had this entire thing happening in a bulk. Now only difference is this is happening in a droplet that contains I number of donor molecule. Sorry? So what I'm saying here is that in these three possible reaction mechanisms, I'm looking at the rate of change of A star, because A star is the excited molecule, and experimentally I can find the concentration of the excited molecule by looking at the fluorescence. So I'm looking at what is the rate of change of this excited species. Now that excited species decays because of this decay, okay, and this is another pathway. I said there are parallel reaction going on. So here it is like a first order reaction here. Here this depends on the number of molecules of D present. There is I here. So I have ID molecule, right? This I, any of this I can react with this A star. Okay, so the total rate would be I times the concentration of A star. Here we wrote concentration of D times concentration of this, right? So here instead of concentration, we are saying number of molecules of D, which we say as a finite number I. Which one? Come again? Because I'm saying that now I'm writing this expression for each of them individually. I got so many droplets. Each of the droplet I say based on how many number of D is present. Like I said, this I means number of D molecule present in a droplet. So instead of giving a droplet 1, 2, 3, 4 all the way, that will be very large. We say what would be the fraction of droplets. Let's say you have 100 droplets. There will be some fraction having 0 molecule of D. There will be some other fraction having 1 molecule, 2 molecule. So I'm writing differential equation for each of those class of droplets. Okay, so that's why we have a suffix I here. In the deterministic case, we don't have this because it's a one single system. Now the entire system is broken into several parts, right? Outside, yeah. Okay, don't confuse between this side and this side. Oh, you're talking about here, right? Okay, yeah, you're right, yeah. Yes, I agree, yes. Oh, that was your question from the beginning. Okay, good. Okay, so what all we are saying is that what we predicted from deterministic approach is what we get for an individual droplet. But the total fluorescence intensity comes from the sum of all the droplets. Okay. We are not discussing the instrumental aspect of it. Let's say there is some instrument that measures fluorescence. Okay, that is not our scope now. Now, if I look at this, okay, this is interesting term. This term tells you that in a droplet containing I number of D molecule, what is the concentration of excited molecule at time t equal to 0, like initial condition. Okay, so now we are going to make an assumption that the initial distribution here is Poisson distributed. So this A star is the total concentration times suppose in this reaction, this D, this is the concentration of the donor, okay, and let's say this is the concentration of the micelles or the reactor. Remember, these are nano reactor. I said there are many of them. So imagine the concentration of the micelle is represented as M. The ratio of D by M will tell you what is the average number of molecule present in one reactor, isn't it? This entire donor molecule is distributed into this many concentration of this many number of micelles. Okay, this basically is a number ratio, number of molecules of D by the number of micelles. Now, if the number of D molecules is smaller than number of micelle, then the average is less than 1. That means there may be many micelle without any D also, and that is what happens typically in experimentally. In the bulk concentration level, D may be finite, it may be about 1 millimolar or 1 micromolar. But then if you look at the partitioning of this D in a reactor, in a micelle, it may happen that this number is less than 1. When the average is less than 1, and if you look at what is the probability of distribution, then you can see that this distribution follows a Poisson process. Here I am talking about a time t equal to 0. When you actually make the solution, you mix the surfactant, you put the D molecule, you put the A molecule, everything, even before you excite it. In the beginning, the distribution of donor molecule into the nanoreactor is a Poisson process. Why we say that? Because the average number of D molecule per micelle is less than 1. Okay, so then you would expect statistically that there will be micelle with no reactant, 1 reactant, 2 reactants, so and so, but then it's going to follow a Poisson process. And this Poisson process is time independent because this is a static distribution. This is a time t equal to 0. Okay. Now, how does it help? Now, this is the total concentration of A in the time t equal to 0. This is distributed as per this Poisson distribution. Okay. So, now what we are going to do is we are going to substitute this in this initial condition. So, the value will change because of this molecular treatment. Yeah. So, we just notation wise we kept as kq, but the actual values are going to be different now, values and dimensions. So, I take this, by the way, this is a function of time t. So, I am interested in A star as a function of t in ith droplet. This is equal to the total concentration A star at time t equal to 0, then the average number of D molecule power I by I factorial e power minus nd times this exponential term. Now, what we will do is we will sum over all possible I going from 0 to infinity, okay, on both sides. This is going to come out. This also will come out, and e power minus kft will also come out. These are all constant terms, they won't come in the summation. So in this expression, we have to deal with this particular one because this one has a summation. What I am doing is I am trying to write this term little differently, that I combine all the term there where to which I can be the power. So I see that nd power I, and then I bring this e power minus I k t also. So I can write this whole power I divided by I factorial, and this is nothing but in this form, okay, which is nothing but e power x. So we get e power whatever you have in the bracket here, that would be e power nd e power minus kt. So we can substitute that for here. And if you look at this, this is the total concentration of A at time t in the entire system. This is what we are measuring as a fluorescence, the total fluorescence summed over all the micelles. This is the total initial concentration, and then we have e power minus nd e power minus kft, then e power this term. So we get a double exponential here, exponential of another exponential. So this would be based on the Poisson distribution that we assumed. And the deterministic model gave us that A star of t is given by A star 0 e power minus kf plus d kq_t. This is a strictly an exponential decay for the deterministic case, but when you take into account of this unequal or inhomogeneous distribution of donor molecules and reactants, we get a double exponential term. Okay. Then I don't know if you can see the picture here. So you see there is a fluorescence decay, and this is not exponential, it's such a stretched exponential. Okay, it has a double exponential character, and you see there are data points which are shown, those are experimental data point, and the curve that you see here, that is the fit to this equation. This equation cannot fit the data. Okay, so a deterministic approach assuming uniform distribution does not work, but if you put this stochastic or statistical distribution of donor molecule, and then when you do the same in terms of mathematical analysis, the same thing, we are not introduce anything else except that we take into account of the non-uniform distribution of the molecules. Okay, so then we get this expression, and this nicely fits at two different. So there are two curves. These actually correspond to two different donor concentrations. That sorry. No, because I am summing over all the I already see, so that I get the total response, total fluorescence response. If you look here, this quantity is known to us. Okay, initial molecular species A we know, ND also we know because this is a average number of molecules of D based on the donor concentration and micelle concentration. This also we know. What we don't, by the way, this should be KQ. Huh? Oh, all the way from here. This should be KQ here. Yeah, sorry. Somebody should have pointed this out. Oh. KQ. KF, KQ. These are all fitting constants. Okay. If you want to get Kf independently, you can also do this experiment without a donor. You look at the natural decay, photo decay of the molecule. Kf can be independently obtained. Then you are left with only one fitting constant, which is Kq. Everything else is a parameter. Nd is a parameter. You can control experimentally. Put more D, less D. This will change. Change the concentration of the micelle. It will change. Similarly, the initial amount of A, how much you want to put, that also is something a variable. A is variable. Nd is variable. Kf can be independently found, Kq can be fitted, and that's what the fit was. Okay, so now I will also give you some details of all the chemistry. I mean, what is this all about? The molecule that we are talking about has a very interesting structure. So this is called something called tris bipyridine ruthenium chloride. Okay, very bulky molecule. So this entire thing forms a complex. This is 2 plus, and there is a 2 chlorine molecules forming a complex. Okay, so this is our molecule A, by the way. Okay, so this is A, and the D, the donor that we talked about, he is called N-methyl phenothiazine. NPTEL. Apparently, it's a very standard set of molecules to study fluorescence decay in chemistry. And the micelle that we talked about, that is called TT OES. So this is tetra decyl trioxy ethylene sulfate. This is the nano container, the micelle that I was talking about. This is the surfactant that is used in this experiment. I have given the the derivation and the notes and references all in my notes. You can also look into it. But I want to bring this to this class because this is something realistic. People do this kind of study, and they do use this statistical distribution of molecular species in a nanoreactor system like this. And we don't have a choice. We cannot do deterministically this problem. No way. Right? And we already saw that the experimental data does not follow simple exponential decay. Okay, so you can clearly see that. There are some problems where the only way to do this is probabilistically or stochastically. Okay, this is one example. Because D is Poisson distributed, A star is also Poisson distributed. Because for the complex to happen, you need some donor in the presence. When you have hundreds of molecules, not all of them get excited. Only some of them get excited. So A star is not necessarily the initial composition that we have. Okay, only some of them get excited. Who gets excited depends also on the local environment and how many D molecules are present. So that's why we assumed that the A star is coupled to the initial distribution of D also. in this particular model. In fact, this is a very, very simplified model, by the way. I have kind of not considered several other decay mechanisms, okay, but those mechanisms can be deterministically dealt with. The key ingredient in this problem is this unequal distribution of the donor molecule, which affects the photo decay of the molecule. Okay, so that's a key thing.